Hello everyone, my name is Dr. H.S. Madhusudan, Assistant Professor of Mathematics. I welcome you all to this series of lectures on sequences. This is a BSc program of University of Mysore, Mathematics 5th semester. Title of the paper is Real Analysis 2 and Algebra 3, and this is session number 7. First of all, relax. Close your eyes and take a deep breath and listen to me carefully. To understand any subject, especially science subjects, a level of concentration and also dedication are needed. Most importantly, interest. So, forget all that is going on in your mind except mathematics and concentrate. Our aim is to develop tools to study, to check whether the given series converges or diverges. But what is a series? Series is nothing but a special type of sequence called sequence of partial sums. So all the properties of sequences also applies to series. So in order to explore series, we need to acquire the knowledge of sequences. Now, let us remember what we have learned so far. First, we defined a sequence, bounded and unbounded sequences, infimum and supremum of a sequence, limit of a sequence, very important definition. Using limit of a sequence, we defined convergence, divergent, and oscillatory sequences. And then we learned some properties of sequences, such as limit of a sequence, if it exists, is unique. Every convergent sequence is bounded. If all the terms of the sequence are positive, and if the sequence converges, then the limit is also positive. Lastly, we proved algebra of limits. Right? Okay. Now, open your eyes and listen to me carefully. Watch the video very carefully. Concentrate. Whenever you get some doubts, repeat the video. Take a paper and a pen. Work out the steps. Now, let us define another important sequence called monotonic sequence. So now, what is a monotonic sequence? So there are four definitions. First definition, if we say that a sequence xn is said to is monotonically increasing. Monotonically increasing if n is greater than m, implies xn is greater than xm for all n comma m belonging to capital N. That is, n and m are positive integers. Xn is greater than or equal to x. So xn is said to be monotonically increasing if n is greater than m, implies xn is greater than or equal to xn for all n comma m belonging to n. So second definition, a sequence xn is said to be monotonically decreasing. Monotonically decreasing if n is greater than m, implies xn is less than or equal to xm for all n comma m belonging to capital N. So here it is greater than or equal to for monotonically increasing, and for monotonically decreasing, xn is less than or equal to xm whenever n is greater than m. Third one, a sequence xn is said to be monotonically strictly increasing. Monotonically strictly increasing if n is greater than m, implies xn is strictly greater than xm for all n comma m belonging to capital N. And lastly, a sequence xn is said to be monotonically strictly decreasing. Monotonically strictly decreasing if n is greater than m, implies xn is strictly less than xm for all n comma m belonging to capital N. Okay. Now let us give some examples. So first one, consider the sequence n. Consider the sequence n. Now what is xn? Xn is equal to n. And what is xm? Xm is equal to m. Right? So now if n is greater than m, means n means what? Xn. So xn. M means what? Xm. So xn is greater than xm. So whenever n is greater than m, xn is greater than xm. So therefore the sequence n is monotonically increasing. Now second, consider the sequence n square. Here, what is xn? Xn is equal to n square. And what is xm? Xm is equal to m square. Now if n is greater than m, implies n square is greater than m square, squaring both sides. Now what is n square? N square is xn, which is certainly greater than m. What is m square? It is x. So therefore xn is greater than xm whenever n is greater than m. Now let us take third example. Consider 1 by n. Sequence 1 by n. Here what is xn? Xn is equal to 1 by n. And what is xm? Xm is equal to 1 by m. Now if n is greater than m, then 1 by n becomes less than 1 by m. Why? When we take the reciprocal, greater than becomes less than, right? So therefore, when n is greater than m, then 1 by n is less than 1 by n. But what is 1 by n? 1 by n is xn, less than. What is 1 by m? It is xn. So therefore, whenever n is greater than m, xn is less than xm. Therefore, sequence 1 by n is monotonically decreasing. Monotonically, strictly decreasing. Right? Okay. Now, let us prove one important theorem. Statement of the theorem is like this. Every monotonically increasing sequence very monotonically increasing sequence which is bounded above converges. So, statement of the theorem is if xn is a sequence which is monotonically increasing. See, monotonically increasing is denoted by upper arrow. And for monotonically decreasing, we use downwards arrow. Okay. So if xn is a monotonically increasing sequence and bounded above, then it converges. So that is the statement of the theorem. Proof. Now given sequence xn is monotonically increasing. Sequence xn is monotonically increasing. Means what? N is greater than m implies xn is greater than or equal to xn. Right? Now, given that xn is bounded, sequence xn is bounded. Therefore, there exists a positive real number k such that modulus of xn is less than or equal to k for all Now let us prove the theorem. Proof. Let xn be a monotonically increasing sequence and it is bounded above. Bounded above, monotonically increasing and bounded above. Let capital M be the least upper bound of sequence xn. Let capital M be the least upper bound of xn, sequence xn. Why? Because xn is bounded above least upper bound exists. Also, given that sequence xn is monotonically increasing, this implies whenever n is greater than m, xn is greater than or equal to x. Okay, these two are given. Now, since m is the least upper bound for any epsilon positive, m minus epsilon cannot be an upper bound, cannot be an upper bound of the sequence xn, right? M minus epsilon is not an upper bound of xn means what? There exists a positive integer m such that there exists a positive integer m belonging to n such that xn is certainly greater than m minus epsilon, right? M minus epsilon is not an upper bound. So therefore, there are some terms of the sequence which are greater than m minus epsilon. If all the terms of the sequence are less than m minus epsilon, then m minus epsilon would have been an upper bound. But it is not an upper bound. Therefore, there exists at least one m belonging to n such that xn is greater than m minus epsilon. So now, if n is greater than m, then if n is greater than m, then xn is greater than or equal to xn, which is greater than m minus epsilon. Why? Because xn is monotonically increasing. So therefore, whenever n is greater than m, xn must be greater than or equal to xn. So therefore, m minus epsilon is less than xm, which is less than or equal to xn, and xn is less than or equal to capital M, because m is the least upper bound. Therefore, m is also an upper bound, and this is certainly less than m plus epsilon, because epsilon is a positive real number. M must be less than m plus epsilon. This is true for all n greater than m, right? So this implies m minus epsilon is less than xn, and xn is less than m plus epsilon. And this is true for all n greater than m. Now, remove m here and here. So we get minus epsilon is less than xn minus m less than epsilon for all n greater than m. That is modulus of xn minus m is less than epsilon for all n greater than m. So this implies limit of xn tends to infinity is equal to capital M. So this shows that a very monotonically increasing sequence which is bounded above converges to its least upper bound. Similarly, let us prove the next theorem, which states that theorem 2, Every monotonically decreasing sequence, monotonically decreasing sequence, and bounded below converges. Now, proof is very similar to the previous theorem. Here we take the greatest lower. So let us consider a sequence xn which is monotonically decreasing and it is bounded below. Okay. Let capital L be the greatest lower bound of sequence xn. Now, for any epsilon positive, L plus epsilon cannot be a lower bound. Why? Because L is the greatest lower bound and therefore any number greater than L cannot be a lower bound. So L plus epsilon is greater than capital L and hence L plus epsilon cannot be a lower bound. So it is not a lower bound means what? There exists a positive integer m such that xm is less than L plus epsilon. L plus epsilon. Now, if n is greater than m, then xn is less than or equal to xm. Why? Because sequence xn is monotonically decreasing and hence whenever n is greater than m, xn is less than or equal to xm. Now, xn is less than or equal to xm and xm is less than L plus epsilon. This is true for all n greater than m. But L is the greatest lower bound. So therefore, here we have L is less than or equal to xn and which is less than or equal to xm, which is less than L plus epsilon. This is true for all n greater than m. But L minus epsilon is less than L. So therefore, L minus epsilon is less than L, which is less than or equal to xn, which is less than or equal to xm, and which is less than L plus epsilon. This is true for all n greater than m. So this implies L minus epsilon is less than xn, which is less than L plus epsilon, and this is true for all n greater than m. Again, in the previous case, we can remove this L and we obtain minus epsilon is less than xn minus L and which is less than epsilon for all n greater than m. Hence, modulus of xn minus L is less than epsilon for all n greater than m. So this implies limit of xn as n tends to infinity is equal to L. So therefore, a very monotonically decreasing sequence and bounded below converges converges to its greatest lower bound. Okay. Lastly, we prove theorem 3, which states every monotonically increasing sequence which is not bounded above diverges to infinity. Diverges to infinity. Proof. Suppose xn is monotonically increasing and it is not bounded above. Bounded above. Then for all k greater than 0, however, however large, we can find a positive integer m such that xm is greater than k. Because it is not bounded above means even any k greater than 0 is very, even though it is very large number, we can find m belonging to n such that xm is greater than k. Right? Now, if n is greater than m, then xn is greater than xn, which is greater than k. Why? Because xn is monotonically increasing, and therefore, given any k positive, however large, we can find a positive integer m such that xn is greater than k for all n greater than m. So this shows that limit of xn as n tends to infinity is equal to infinity. So therefore the sequence xn diverges. So lastly, if a sequence is theorem 4, if a sequence xn is monotonically decreasing and not bounded below, then it diverges to minus infinity. So this is very similar to previous theorem. We can prove it. Okay. Thank you.